In this lesson, we're going to be discussing implicit differentiation. Now, what exactly is implicit differentiation and when do we really use it? Now, up to this point, you've been working with derivatives, with derivatives of functions written in using their explicit equation. Now, an explicit equation is when the function is written as y equals to a function of x. So that is an explicit equation. It's when, for example, you have a y equals to 2x squared plus 1. You'd notice that you'd have y written as a function of x. So you'd have the dependent variable written in terms of the independent variable. However, what are implicit equations? Implicit equations are equations that are written in terms of x and y, but however, we cannot really write y in terms of x or using an explicit form of the equation. If you look at the equation I have here, x squared plus y squared equals to 1. Now, x squared plus y squared, now y is still a function of x. Y is still a function of this variable x. However, I do not have the equation written as y equals to an expression in terms of x. Now, over here, you could think of possibly solve for y, but solving for y and y being squared would actually lead you to two possible expressions from the plus or minus the square root of the expressions, and sometimes you cannot even solve for x. It really depends on the given implicit equation. So this is when it's easier to use implicit differentiation in order to determine the gradient of that curve at a given point. So over here I have a circle of equation x squared plus y squared equals to 1, and I need to determine the gradient of that circle at the point 0, 1. So since over here there's no way to split the x and the y and write the equation in its explicit form, in this case your derivative expression will be in terms of both x and y. So this is why here, in order to determine the gradient at a given point, I need both x and y values, unlike when the function is given in its explicit equation. So over here, we start with the implicit equation of the curve, x squared plus y squared equals to 1. And we start differentiating both sides with respect to x. So x squared, what's the derivative of x squared? The derivative of x squared is 2x. However, regarding the derivative of y squared, y being a function of x, the derivative rules still apply. However, y being a function of x, we'd have to apply the chain rule here. We know that if this is in the form u squared, where u is a function of x, then the derivative would still be 2 times u, but we do not forget to multiply by u prime, which is the derivative of u with respect to the variable x. So over here, y squared, we see it exactly as u squared, a function of x squared that I need to find the derivative to. So the derivative of y squared is 2y. And using the chain rule, we multiply by the derivative of that expression with respect to x. And the derivative of y is dy over dx, which is the derivative we're looking for. So equals, and now I differentiate this right-hand side with respect to x, and the derivative of 1 is 0. Now watch out, if you have variables on the right-hand side, you'd have to find their derivatives. The right-hand side here is not always 0. It happened here that it's 0 because the right-hand side is constant. So since I need to find the gradient, I solve for dy over dx. So 2y times dy over dx is negative 2x. So dy over dx would in fact be negative x over y. So that is the expression of the gradient in terms of x and y. Now I need to find the value of the gradient at the point 0, 1. So dy over dx evaluated at the point 0, 1. At the point 0, 1, so in the expression of the gradient in terms of x and y, I replace x by 0 and y by 1. So it's negative 0 over 1, which is 0. So the circle has a gradient of 0 at the point 0, 1. So this is in fact the process of implicit differentiation. Implicit differentiation is when you get to find an expression of the derivative in terms of x and y using these implicit equations. In this second example, I already have here another implicit equation. You'd notice this is not written in the form y equals to an expression in terms of x, and there's no way I could solve for y and write an explicit equation. So this is an implicit equation where I need to apply implicit differentiation in order to determine dy over dx, the derivative of y with respect to x. So I start term by term on each side. X cubed has a derivative of 3x squared. Y cubed has a derivative of 3y squared. However, using the chain rule, since y is an expression of x, I have to multiply by y prime, where y prime is in fact dy over dx, minus 9 into. Now, x times y can in fact be seen as a product in the form u times v. So the derivative of u times v is u prime v plus v prime u. So if u is x, then u prime is 1. If v is y, then v prime is dy over dx. It's y prime, which is dy over dx. So applying the derivative, the product rule for derivatives here, so u prime v, so it's 1 times y, which is y, plus v prime times u, which is x times dy over dx. So that is regarding the derivative of the right-hand side, while the derivative of the left-hand side, which is 0 here, because the derivative of 0 is 0. Now, in order to find dy over dx, I need to expand everything and group the terms in dy over dx on the left-hand side and everything else on the right-hand side. So it's 3x squared plus 3y squared dy over dx minus 9y minus 9x dy over dx. So these are the two terms in dy over dx that I need to group on the the left-hand side, and then everything else on the right-hand side. So it's 9y minus 3x squared. Sorry about that, my pen slipped. Okay, so dy over dx, the derivative of y with respect to x is 9y minus 3x squared divided by 3y squared minus 9x. And over here you notice I have a 3 as a common factor, so I cancel everything by 3, so it's 3y minus x squared divided by y squared minus 3x. So that is the derivative of y with respect to x of this implicit equation. So whenever you have an implicit equation that you need to find the gradient to or the implicit derivative to, all you need to do is just differentiate both sides with respect to x, keeping in mind that the terms involving y, you need to apply the chain rule. So the derivative, for example, here of 3y squared, y cubed is 3y squared times y prime, where y prime is dy over dx. And whenever you have a product of terms in x and y, you'd have to apply the product rule. Similarly, if you have a quotient of terms in x and y, you'd have to apply the quotient rule. So that is it regarding implicit differentiation of functions given their implicit equations.